I'm going to talk about constraint satisfaction problems. For example, say you have the map of Australia here, and the task is to color each region either red, green, or blue, and no adjacent region can have the same color. Those are constraints, and that's a constraint satisfaction problem. So a constraint satisfaction problem, we've seen so far, if you've been following the videos, other algorithms that we evaluate states with heuristics and a goal, right? A constraint satisfaction problem is a factor representation of a state where you have a set of variables with a value. The idea that you have constraints now that allows for more efficient algorithms. And we want to find any solution now. There isn't an optimum, there's a solution, okay? And either they have a solution or they don't, okay? In the way of constraint satisfaction problems we're going to see now. There's another variant of constraint satisfaction problems in which there's an ideal solution, but if it cannot be found, there's a second best. We're going to talk a little bit about that in future slides. Excuse me. Well, the constraint satisfaction problem have a formulation. Usually there's a set of variables, a set of domains for each variable, and a set of constraints that might involve these variables. Okay? So I'll explain a little bit what each one of these is, right? So x is a set of variables that goes from x1 to xn, so all the variables in your program, in your problem. D is the set of domains, so basically for each of these variables, what are the possible values they can take, okay? So there's a domain sub I for each x sub I, okay? And then there's a set of constraint, which is basically the scope, what are the variables involved, or what's the scope involved, and what is going to be the relationship between those variables. Okay? Usually we won't do the notation where we put scope, comma, relationship so much. We'll just put some constraints, but we'll start with the Australia problem. The idea is to color each region of Australia with a different color, and no adjacent regions should have the same color, and you only can choose between red, green, or blue. Another way of looking at this problem is to put it as a graph, where you have Southern Australia here, and Southern Australia is connected to Western Australia, the Northern Territories, Queensland, New South Wales, and Victoria, right? And Tasmania is unconnected to any of these, right? And then perhaps by looking at it as a tree, we can use, looking at it as a graph, we can use some of our search problems to help us guide through this. But let's look at the formulation. You have the variables. The variables are the different states: Southern Australia, New South Wales, Northern Territory, Western Australia, Queensland, Victoria, and I forgot Tasmania right there. But let's think that Tasmania is now there. It should actually appear anytime now. So these are the variables. Now you see that there's also the domain. Whoops. Fine. All right, there's Tasmania. Okay, so then there's also the domains. So for each of these, so for example, for Southern Australia, the choices are red, blue, or green. These are the values that each one of these can take. Now, in this problem, each variable can actually take the same colors initially, right? So so that's the domain of the variables. Okay. Now, the constraints. Well, the scope is for all variables, okay, x sub I, such that x sub j is touching for all pairs of variables xi, xj, such that they're touching each other. Okay, that's the scope. And the constraint is the color of the one should be different than the color of the other. Okay, so this is a way of describing a set of constraints. Okay. Let's look at another problem. For example, scheduling classes. Okay, how do we formulate a program about scheduling classes in terms of variables, domains, and constraints? Well, one way of doing it is, for example, if you take, these are the computer science classes. These each class is a variable. And then the domain is the classes, the times, the days and times at which these classes can actually happen, right? So, for example, for CS235, it can be Monday at 9 a.m., Monday at 11 a.m., Monday at 1 p.m., and so on and so forth, right? So these are days in which classes can happen. And we can formulate the following constraint. For all ij, if the variable, if the classes of xi and xj are co-requisites, then the times must be different. If they're not co-requisites, well, then they can happen at the same time. That can be one way of formulating this problem. Now there's another concept called the Auld diff that might help us develop constraints. So for example, we have Sudoku here, in which this space has to be different than this space, has to be different than this space, and so on and so forth, right? Well, instead of putting many constraints, instead of putting like, I don't know, how many constraints, we can do Auld diff. And we can do, there's an Auld diff for the columns, that's 9 Auld diffs for the columns. Then there's an Auld diff for the rows saying all the numbers here must be different, right? So that there's 9 Auld diffs for the rows. And then there's also an Auld diff for each square. Okay, so within a square, each of these variables, which is a slot in the Sudoku puzzle, each of the variables should be all different, right? So there's 9 in the squares, and that gives us a total of 27 Auld diffs. It's a lot less than, say, the simpler way to put this is 81 pairs, difference, but then it's a lot more because you have to consider this square, and not only for each square, you have 80 possibilities. So there's a lot of constraints in here if you start computing them. Okay. All right. Now there's other kinds of puzzles. Usually they're called the Crypt arithmetic puzzles, where the problem is like this. So they say 2 plus 2 is 4, and all these letters stand for a number. Okay? So one can think of the constraints as follows. F, T, U, W, R, O, they're all different. All the unique letters here are all different. They're all different numbers. And then also we know that O plus O is R, right? O plus O is R. But what if O is, say, for example, 7? 7 plus 7 is 14. So R would be 4, and the 1 gets carried over here, right? So instead, we can say that O plus O is R plus 10 times the carry, okay? So O plus O is R plus 10 times the carry of the tens, right? So if O were to be 7, we have 7, and 7 is 4 plus 10 times 1, right? Because the carry is 1, R is 4, plus 10 times 1, that's 14, right? So one can say that O plus O is R plus 10 times the carry. In the same way, one can say that W and W plus this carry is U, right? And then, but perhaps there's a carry to this side as well. What if W and W are 7? So 7 plus 7 is 14, plus the 1, that's 15, that's U is 5, and there's a carry. But this carry is now in the hundreds. And the same thing is going to happen with T and O. So the constraints stand like this. O plus O must be R plus 10 times the carry. Now, that carry, if present, right, plus W, so I'm looking at this column right now. Okay, W plus W must be U plus 10 times the carry of 100s. In the same way, we can see that then the next time around, we're going to have for the t's, right? So let's look at the t's now. We're looking at this column here, right? T plus the carry of the hundreds, so the second carry, right? Plus the carry of the hundreds must be O. So the carry of the hundreds plus T must be equal to O plus 10 times the carry of the thousands, which basically these numbers, they don't denote much except which place the carry is on. And then F must be the carry of the thousands because there's no letters above F. Okay? That's how we could specify the constraints. Here I'm not doing it in the form of scope, comma, relationships, right? I'm not doing it like that. I'm just doing the relationships, and the scope is the variables involved here, right? So for example, the scope of this constraint would be the values O and R, right? And then I introduce this C10. And from now on, the constraints, I'm going to just put the constraints like this. Another way of representing this is, for example, in a tree where this square is the all diff. These are all different. And then F and T, you know, they're added together and they go into another constraint, which is they together have C3. They together create another variable to which they're that is involved in this constraint. For example, F and T are involved there. U and W, right, are involved, right? U and W are involved. U and W are involved in this constraint. U and W are involved. And they also involve C of 100 and C of tens. And they also involve the second carry and the first carry. The first carry is C of 10. The second carry is C of 100, right? So this basically has a graph that tells you which variables are involved. This is C of 100. This is, I denoted these. I'm sorry, this is C of 10. C of 10, this is C of 100, I also called it. And this is C of 1000. It's the same, they're the same variables. Okay? So this is another way of writing, of specifying a constraint satisfaction problem that goes like that. Now, constraint satisfaction problems, there's a kind of constraints, different kinds of constraints. So the unary constraints involve a single variable. So for example, the colors in the Australian map, right? So southern Australia cannot be green, or southern Australia cannot be purple because the colors are green, blue, and red. A binary involves a pair of variables. So for example, southern Australia cannot be of the same color, the same assignment as Western Australia, for example, right? And then there might be a higher order which involves 3 or more, which are the ones that we just saw in the Crypt arithmetic puzzle. Well, we can search if we have a way of searching this, right? We can do a depth-limited search with a constraint in a constraint satisfaction problem with n variables. Okay. So, for example, in the Australia, we have 6 variables for the 6 states, and each state has a domain size d. In the Australia puzzle, this is 3, right? The branching factor at the top is going to be n times d because all assignments are possible for all variables, right? Now at the next level, you can have one less assignment, you know, times the domain size, right? Because you assign the first one and then the rest can only have one less assignment, right? And in the end, you end up with n factorial times d to the n leaves in this tree, okay? Now, only d to the n possible assignments are complete assignments, right? So this is clearly a such problem that we have to optimize somehow. So one way of doing this is via backtracking and noting the following. The variable assignments are commutative. So if I say Western Australia is red, and that implies that Northern Territories is green, this is the same as if Northern Territories is green implies that Western Australia is red. They're commutative, so this factorial is reduced now, right? If we only consider one combination, right? We're going to try to consider assignments to a single variable at each node, And then what happens is that if we find an inconsistent or an illegal value on an assignment, we'll backtrack. Okay? This can solve the n queens for n approximately 25. For more values, it doesn't quite solve it. We'll see that in a bit. All right. So backtracking, the algorithm for backtracking is basically a depth first visit on the assignments. But here's the important lines. If the value is consistent with the assignment, then we add this value to the assignment. Okay? Then we do all possible inferences in our tree, because, for example, if we have the Australia puzzle here, right? And we assign some color here, and some color here, and some color here, we can infer what the color should be here, right? Or if we assign two colors, because there's only two colors, we can already infer what this color is going to be, so we don't need to actually make it part of the assignment, right? We just do all the possible inferences, and then we continue with the next variable, which would be this one to assign, okay? That's the idea of this. That's one important point of this tree visiting. Okay, we do the inferences. If we encounter that the inferences are going to lead to a failure, I mean, if the inferences do not lead to failure, we're going to add all the assignments that we've inferred to the global assignments. Okay, and then we will just recursively call this function. Now, at the end, once all the assignments are done, if the result is not a failure, then return that result. Now, if this condition fails, or this condition fails, or a value is not consistent with the assignment, right, then other values are going to be tried. Once all the values are tried and nothing is consistent, what happens is you're going to remove that value, right? We're going to remove that value and inferences from the assignment, and we're going to start, we're going to start with the next one, and so on and so forth. If all else fails, then we'll return failure if no solution is found. For example, let's start with this map, right? The map of Australia. And we have all of our choices here, right? We have red for Western Australia. Let's start with Western Australia first. Okay, that's the state that we're looking at right now. Now, we have these three possible assignments. Let's look at this branch now. Okay, now we're gonna not only Western Australia, but now we're gonna assign the Northern Territories color. Now, so far so good. Let's continue with the possible assignments for this one. So then we want to assign Queensland a color, right? Here's an interesting thing. Yeah, we can assign Queensland a color, right? Red or blue. And if we were to follow this one, if we were to make inferences here, right, it will infer something that's illegal. There's no color that can go here, right? So once the inferences are made after we assign this color, we will never pursue this branch, okay? We'll only pursue this one. And if we find something, if we find something that's illegal, again, we'll backtrack and not pursue this one. We'll pursue others, okay? However, there are many ways in which this can be optimized. For example, when we're at this step, right, it might be advisable to assign the color for the Southern Australia province, okay? It might be useful to assign this one because this one is the one that's going to get us more bang for the buck. If this is, say, cannot be green, cannot be red, there's only one color for this guy, where there's two colors for this state, right? This one can be in the case that it's green, this one can be blue or it can be red. But this one has only one possible assignment. Perhaps we want to just assign this one and then continue. That way, the tree is gonna do a lot less backtracks in the future. So, as I just illustrated, it's really important to know how to choose the next variable that you're going to test. One way of looking at this is to choose what's going to become the minimum remaining value. So let's look at a variable, or MRV. Let's look at, this is a heuristic that is going to look at the value with the fewest legal values. In this case, right, Southern Australia is the one with the fewest legal values at this step, because it can only be blue, right? So there's one legal value, where this one has two legal values. That's the minimum remaining values. It really improves the search a lot. There's degree heuristics. Basically, pick the variable that's involved in most constraints, because if you pick that variable, you already reduced the domains on the other variables, right? So if I pick, again, degree heuristics is similar. This one is the one that's involved with more states here, because almost all states but Tasmania touches Southern Australia. So maybe I want to pick this value first, actually. I could start, instead of starting with Western Australia, I could have started with, immediately started coloring this South Australia right away. So then I have less choices for these others, and the tree might be smaller. And then there's another one that looks ahead, another heuristic that is used. That's the least constraining value. The idea here is to look, what are the ones that are going to have the most slack in terms of values that I can assign to them, right? And then the thing is that this looks ahead a little bit and will prefer the trees that generate more flexibility for the future. Now we can always have check for constraint consistency, and we can do, this is called inference. So we always, whatever assignment we do, we try to infer whether it conflicts with something else. And one algorithm to do this is the arc consistency 3. This is AC3. This is an algorithm from the 70s. It's called 3 because on the paper that it was published, this was the third algorithm. And it's easy, you can look for this in Wikipedia. It makes a lot of sense. It has a stack with pairs of linked nodes. So as soon as a constraint satisfaction problem is represented as a graph, okay, then we want to find the consistency between these arcs. There's another way of improving the tree exploration, and that's called forward checking. And this really saves a lot of time. And forward checking, what it does is basically it looks at each variable x in the constraint satisfaction problem, and for each variable, for each unassigned variable, okay, y, that it's connected to the variable that I'm examining right now, and for each of the values d in the domain of that variable, I will see if d is inconsistent with the value that I've assigned x, then I'll take that value from the domain. And then I'll do this for every variable. Every time I do an assignment, I'll pass the constraint satisfaction problem with the assignments as a forward checking. I will check and reduce the domain of the variables that would be in conflict. And then I'll return the new CSP with the modified domains. For example, let's say we have the Australia map, right? So the Western Australia, Northern Territories, Queensland, New South Wales, Victoria, South Australia, and Tasmania. The domain for all of this is red, green, or blue at this point. But now let's assign red to Western Australia. So after Western Australia is red here, right, then the Northern Territories can only be green or blue. Queensland can only be red, green, or blue. The New South Wales can be red, green, or blue. Victoria, red, green, or blue. Now South Australia can be only green and blue, and Tasmania can be any color. So then we assign, for example, Queensland green. Okay, Queensland green. Now the Northern Territories can only be blue. New South Wales only red and blue, and South Australia only blue. Then we'll assign Victoria blue, right? So one of these. So I'm keeping assignments here that I know what are all the possible assignments, so I don't have to explore them all, right? So then I assign Victoria blue, for example, here, right? And so on and so forth. But we realize one thing here. There's no possible domain here in South Australia. This is failure. If the forward checking finds no potential domain, no domain variables in one of no domain values for one of the variables, okay, then it's a failure, right? And then if it returns failure, our algorithm should backtrack as well. Now, one last algorithm in constraint satisfaction problems, one last consideration is that we can change variables using heuristics, but one heuristic that is very useful is the one of minimum conflicts. We want to check which assignments, which values of assignments produce the minimum amount of conflicts, okay? So in this way, and we can check this for a number of steps before giving up, okay? Otherwise, we might be doing this for a while. And the idea here is that we will look at variables, we will look at current assignments, okay, to see if they're a solution for the constraint satisfaction problem. If they are, the assignment is a solution, then return it. If not, we're going to create a variable that is going to be a randomly chosen conflicted variable in CSP. We're going to look for a conflicted variable in this assignment, okay? And for this value, we're going to look at that variable and we're going to pick the value that minimizes conflicts. And we'll put that in current. And then we're going to do this for however many steps, right? And at some point, current will be the solution. If not, then we'll return failure. But just doing this algorithm improves a lot of things. So as an example here, we have the 8 queens problem, right? And these are the number of conflicts that I will have if I move the queen at each one of these steps. So of course I want to move it to one of the ones, right? Randomly. I'll move it to this one. Now there's a conflict with this queen. This queen has to move to the point of minimum conflict, and here's a 0, right? This here, the conflict is 0, and I move it there. So by doing backtracking and looking at the minimum number of conflicts to pick the next node, and also doing forward checking, algorithms can be improved a lot. For example, for the n-queen problems, doing a lot of n-queen problems for n, I believe 8 till n is 100, I think. Look at what the algorithms reported here. So just using backtracking, okay? We're going to do the n queens, by the way, I'm sorry. The n queens is 2 queens all the way till 50 queens. So find the solution for all those problems, right? With backtracking, over 40,000, right? So over 40 million iterations, okay? And it could not find the solution. That's why it's in red. Using forward checking for the same problem, again, it gave up over 40 million iterations without finding the solution. Now using the minimum conflicts, it was only 4,000 iterations and it found the solution to all n queens puzzles from 2 queens to 50 queens. Now the same problem that we looked at this lecture with Australia has been proved with the United States states. The idea here for the United States of America is with 4 colors. Can we color all states of the United States of America with 4 colors such that no adjacent state has the same color? Backtracking alone took 1 million iterations and it didn't find a solution, returned failure. Forward checking though, so backtracking with forward checking gives the solution 2,000 iterations. And if you use the minimum conflicts algorithm, it gives you the solution in 64 iterations. Notice there's no k next to this, just 64 iterations. And then there's a very famous problem, the zebra problem, okay, in which the zebra problem goes a little bit like this. Try to solve this problem. There are 5 houses. The Englishman lives on the red house. The Spaniard owns the dog. Coffee is drunk on the greenhouse. The Ukrainian drinks tea, and so on and so forth. They give you 5 houses. They give you some nationalities of the people that are there. You know that the 5 houses, they have people from 5 different nationalities. They're painted in different colors. People smoke 5 different brands of cigarettes, and they drink different things, and they have different pets. So they tell you a little bit about each house or each nationality or each pet or each habit, and you have to figure out where the zebra lives and where people go to drink water. Well, with backtracking, this can be solved in about 4 million iterations. For with checking, 35,000, and with minimum conflicts, only 2,000. So these algorithms do improve on each other and build upon the other algorithms that we've looked in other videos